Hi class, it's me, Mr. Morris again, and this is Unit 3.8. We're talking about representations of solutions. Remember that our molarity equation is moles of solute over liters of solution. Sometimes we represent that as N over V because it's moles divided by volume, but it's specifically moles of solute divided by the volume in liters of solution. We also want to know the formula for diluting solutions. So the molarity of your stock solution times the volume of the stock solution that you use will be equal to the molarity of your diluted solution times the volume of your final diluted solution. Molarity of substance X can be written as brackets around X. That's a way of writing concentration of X, and normally in units of molarity. So we're going to start with an example problem. A student wants to prepare a solution by dissolving 0.250 moles of Na2SO4 to make 0.500 liter solution. So if he wants to do that, we want to know how many moles of Na will be in the solution. To start with that, we know how many moles of Na2SO4 we have in the solution. Just remember that Na+, there are 2 Na+ ions in every 1 mole of Na2SO4. So we're going to have twice as many moles of Na+ as there are moles of Na2SO4. So we'll just take the moles and multiply it by 2 because we've got twice as many moles of Na+ as there are moles of Na2SO4 in the solution, and you end up with 0.500 moles of Na+. What about how many moles of SO4? Well, for every 1 mole of Na2SO4, we have 1 mole of SO4. There's no parentheses with subscripts on the outside, so it's just going to be 0.250 moles of Na2SO4. Because 1 mole of Na2SO4 just contains 1 mole of sulfate ions. So now we want to calculate the concentration of sodium sulfate. Na2SO4 is sodium sulfate. To find the concentration of sodium sulfate, we're going to use this formula up here, moles divided by liters, so 0.250 divided by 0.500. So you end up with 0.500 molar solution. Now we want to know the concentration of Na+. Well, we have moles of Na+ right here. Divide that by the same 0.500 liters solution. You end up with 1 molar solution. And that makes sense because it's twice as much as the answer in part C. 2 times this would give us 1.00 molar. And that makes sense because 0.500 molar Na2SO4 is going to have twice the concentration of Na+ ions, sodium ions. And then sulfate ions is just going to be exactly the same as the molarity here, because for every 1 molar Na2SO4, we have 1 molar SO4 or sulfate ions. All right. Keeping these equations in mind, we are going to do another example problem. A student prepares 100 milliliters of 0.400 molar barium nitrate solution from a 1.000 molar stock solution. So we know the molarity of the stock solution, we know the volume of the diluted solution, and the molarity of the diluted solution. What's the volume of the stock solution? I'm going to be using this equation since this is a dilution problem. So, M stock, we know that it's 1.000. V stock is what we're looking for. The molarity of diluted solution is going to be 0.400, and the volume of the diluted solution will be 100 milliliters. That's what we get right here. Then we would just multiply these numbers, then divide by 1.000 molar to get our volume. It's 40 milliliters, 40.0 milliliters. Now, if I wanted that in liters, I can do the same thing. I just need to convert the milliliters into liters. So sometimes you want to be able to do that. Don't forget to convert to liters. We just divide the milliliters by 1,000. So our problem over here, same numbers. The only difference is this is 0.100 liters instead of 100 milliliters. Multiply and then divide by 1. You end up with 0.0400 liters. Okay, part B asks, what are the concentrations of barium ions and nitrate ions in the stock solution? Well, the barium ions are going to have the same concentration as the concentration of barium nitrate in the stock solution. And the reason is because there's a 1-to-1 ratio between barium ions and barium nitrate. There's only 1 mole of barium nitrate in every mole. There's only 1 mole of barium ions in 1 mole of barium nitrate. So it's just 1.000 molar, so the concentration of barium ions is going to be the same, but the nitrate ions are going to be different. I've got twice as many nitrate ions because of the subscript of 2 here. So it'll be 2.000 molar instead. Okay, part C asks, what are the concentrations of barium ions and nitrate ions in the diluted solution? So now we want to look at the molarity of our diluted solution. Barium is going to be the same again. Nitrate is going to be twice as much. So we get 0.400 molar barium ions and 0.800 molar nitrate ions because our molarity of the diluted solution is 0.400. Barium ions are going to be the same. Nitrate ions twice as much because of that subscript of 2. We get to part D. How many moles of barium nitrate are in the stock solution used? To find the number of moles of barium nitrate used, we're going to take the molarity and multiply it by the volume in liters. So the moles of stock solution is the molarity times the volume, but it has to be volume in liters. So note, the volume has to be in liters. So we get 0.0400 moles. That is the number of moles in the stock solution. Well, how many moles are there in the diluted solution? That's part E. Well, we're going to do the same thing, but we're going to use the diluted values. So that would be 0.400 times 100 milliliters of the diluted solution. So when you do that, you end up with 0.0400 moles. Again, this is the same answer. These are the same because during dilution, the amount of barium nitrate isn't changed. We just added more water. We didn't take any barium nitrate out, and we didn't add any extra barium nitrate. We just added water. That's what dilution is. It's adding more of the solvent. And then finally, we get to part F. How many moles of barium are in the stock solution used? Well, if we have 0.04 moles of barium nitrate, you're going to have 0.04 moles of barium ions. And how many moles of nitrate do we have in the diluted solution? So our diluted solution, that's 0.400 times 0.1000 equals 0.0400 moles of barium nitrate, which is going to be, we're going to have twice as many moles of nitrate ions because we have that subscript of 2. Moving on to another example problem, kind of similar. We have 50 milliliters of 100 molar or 0.1 molar iron chloride solution, iron 3 chloride solution, mixed with 125 milliliters of 0.200 molar iron 3 chloride solution. Okay, this one's actually a little bit more involved. we want to determine the concentration of iron ions and the concentration of chloride ions in the final solution. To do this, we have to first kind of come up with a strategy for how we can accomplish it. What we know is the molarity and the volume of two different solutions. From that, I can find the number of moles, add those together. We could find the total volume by adding the volumes together, and then we could calculate the final concentrations. So our strategy, using the formulas we've been talking about, is first we want to find moles of solute, whether that's Fe3 plus, Cl minus, and the liters of solution for each original sample. The second part, we want to add the liters from each original solution together. So we're going to add up our volumes so that we can put that in the denominator. We want to add the moles of the solute of interest, whether that's iron 3 plus or chloride ions. From each original solution, we're going to add those together. And then we'll find the molarity of each of those by dividing moles of the solute of interest divided by liters of solution. Now let's work through it. We've got two solutions. The first solution is going to be this one here. Solution 2 is going to be this one over here. So the molarity of the first solution is 0.100 molar, and the volume is 50.0 milliliters. Let's turn that into liters. That would be 0.0500 liters. So the moles of FeCl3, if we rearrange this equation, the moles of solute ends up being molarity times the liters of solution. So that's what we did here. Moles of FeCl3 is just the molarity of FeCl3 times the volume in liters of FeCl3. So we get 0.00500 moles of FeCl3. The moles of Fe3 plus is just going to be the same, because for every 1 mole of FeCl3, we have 1 mole of Fe3 plus. We're just going to multiply 1 times the number of moles of FeCl3. What about moles of Cl? So if I wanted to find the moles of chloride ions next, I'm going to multiply this same number here, the moles of FeCl3, but I'm going to multiply that by 3 because of the subscript of 3. So that's what we did. 3 times 0.00500 gives you 0.01500 moles of moles of Cl minus chloride ions. Solution 2, do the same process. We've got our molarity, we've got our volume, turn it into liters. Then we want to find moles of FeCl3 by multiplying those numbers by each other. The molarity times the volume. You get 0.0250 moles of FeCl3. So if I wanted to find my iron 3 ions, it's going to be exactly the same number, 0.0250. Remember, there's 1 mole of Fe3 plus in every mole of FeCl3. So the number of moles of Fe3 plus is identical to the moles of FeCl3. The chloride ions are going to be 3 times as many in this case, because I've got 3 chloride ions in every FeCl3 formula unit. So I end up with a chloride ion, and the number of moles of chloride ions being 0.0750 moles. The next thing that we need to do is add together our moles of Fe and our moles of Cl. That's step 3. We're going to add those together. We're also going to add the liters together. I've got 0.0500 liters and 0.1250 liters. We're going to add those together, and then we can divide to find out what the concentration of each ion is. So let's start with the volume. To find the total volume, volume of solution 1 plus volume of solution 2. 0.0500 liters plus 0.12500, or 0 liters, equals 0.1750 liters. Then we're going to add up the moles of Fe3 plus. To find the total moles of Fe3 plus, we're going to do moles of Fe3 plus in the first solution plus the moles of Fe3 plus in the second solution. 0.00500 plus 0.0250, and we get 0.0300 moles of iron 3 ions. We also want to know the number of moles of chloride ions. Actually, let's start with the concentration, I guess, of Fe3 plus ions. The way you find the concentration once you know the number of moles is you do moles divided by liters. So that's what we've done here. 0.300 moles is the number of moles of ions. And then in the denominator, we're just dividing by the volume of our solution, 0.1750 liters. That's the final volume after we've mixed the two solutions together. And then you get 0.171 molar Fe3 plus. To find the total moles of chloride ions, we add those two together. We got our answers from here and here, add those together, and you get 0.0900 moles of chloride ions. Then the concentration of chloride ions is going to be equal to the number of moles we found here divided by the same volume we had up there, the volume after we add the two solutions together. So that's V1 plus V2, 0.1750. You get 0.514 molar chloride ions. Similar question. Maybe pause the video and try it on your own. Now I'll go through the solution. We've got our equations here that we're going to use. The strategy, step 1, we're going to find moles of solute and liters of solution for each of the original samples. We're going to add the liters of solution from each original solution together. We're going to add the moles of solute of interest from each original solution together. And we're going to find the molarity of the solution by dividing moles divided by liters for each of those ions respectively, in order to find the concentration of sodium, strontium ions, and hydroxide ions. So we've got two different solutions we're mixing together. I've got a sodium hydroxide solution and a strontium hydroxide solution. Start with sodium hydroxide. We've got a concentration of 0.100 molar given in the problem, and 75.0 milliliters. I've just turned that into liters by dividing by 1,000. The moles can be found by multiplying molarity times volume, and we've got 0.00750 moles of sodium hydroxide. From here, I want to know how many moles of sodium ions I have in this solution. Since there's only one sodium ion in each formula unit of sodium hydroxide, it's going to be the same number. Just 1 times the number of moles of NaOH. Same thing with hydroxide ions. There's only 1 mole of hydroxide ions in sodium hydroxide, so we're going to multiply that number by 1 once again. Let's go to strontium hydroxide. Our molarity is 0.500 molar, and we have a volume of 50.0 milliliters. Turn that into liters, you get 0.0500 liters. We will multiply those numbers by each other to find the moles of strontium hydroxide, which is 0.0250 moles. To find the number of moles of strontium ions, we're just going to multiply by 1 because there's only 1 strontium ion in every strontium hydroxide formula unit. So we get the same answer. Hydroxide, on the other hand, has a subscript of 2, so we will multiply that number by 2. 0.0250 times 2 is 0.0500 moles. We just doubled the number of moles of strontium hydroxide because of that subscript of 2. Now we have moles of sodium, moles of hydroxide, moles of strontium, and moles of hydroxide. We want to add up our volumes since we're putting these solutions together. We're pouring them together and mixing them. The volumes are going to be 0.0750 plus 0.0500 liters, so that gives us 0.1250 liters. Then we want to find the concentration of sodium, strontium, and hydroxide ions. Let's start with sodium. First, we need to find how many moles of sodium we have. We would add up the sodium that we see from every part of this. I only see sodium in sodium hydroxide. There's no sodium in the strontium hydroxide mixture, so we don't have to worry about that. It's just going to be 0.00750 moles because there's no sodium in strontium hydroxide. Next, let's find the moles of strontium. Again, there's no strontium in the other mixture, no strontium in sodium hydroxide, so it's just 0.0250 moles. Now let's find the moles of hydroxide. Well, to do that, I have some hydroxide ions in the sodium hydroxide mixture, and I have some hydroxide ions in the strontium hydroxide mixture, so I will have to add these numbers together. The total moles of hydroxide is 0.00750 plus 0.0500, and that gives us 0.0575 moles. Now we can find our concentrations of each ion. I'm going to take the moles of sodium, 0.00750, divided by the liters of solution, 0.1250, to find the concentration of sodium ions. I get 0.0600 molar sodium. Okay, I'm going to do the same thing with strontium now. 0.0250 moles divided by the total volume of the mixture, 0.1250, and I get 0.200 molar strontium ions. And finally, the hydroxide ion concentration is 0.0575 divided by 0.1250, and I get 0.460 molar hydroxide ion solution. So there's a couple different types of fairly challenging concentration problems, but it illustrates some important things. We're going to get into some diagrams in the next video.